work energy theorem and the conservation of mechanical energy. So today we'll take up problems on conservative forces first, and then this time allows conservation of mechanical energy. Okay, so I've selected 3 problems. So here is the first one. This is based on conservative forces. Board is still damaged from yesterday's assault. Okay. So conservative forces. This is example 1. So you're given a force which is a function of x. So here is the force which is a function of x. In a very simple manner, it's c times, c is a constant here, and c is greater than 0. C times x. And in this force field, you are moving an electron. In a closed path. Now, what is that closed path? It's like a square of length L. So you are moving the electron in this force field. The force is an external force, okay? And from the direction, because this is y and this is x, j cap means it's directed where?
Y.
Another positive y, right? And since c is greater than 0, it's positive. So that's the direction of the force. Okay, so what you're doing is you're making the electron move in this force field along this square path. It's a closed path. So you start from the origin 0, 0, and when you hit L, 0, you make a vertical move and reach L, L, and then move on to 0, L, and then come back to the original point. Now we have to find out whether this force F is a conservative force or not.
Yes.
Is it a conservative force already? How do you know?
Calculate, yes, sir.
How do you know this is a conservative force already?
Calculated.
You calculated? Okay. Okay, so let's see whether this name is correct or not. So the name is?
Prithvi.
Huh?
Prithvi.
Vivek.
Prithvi. Charan.
Charan. Okay, Charan's claim. Charan's claim is that it's a conservative force.
Okay.
And what is it that you are betting?
No, sir.
Is
Work
it like a
done.
bet?
No, sir. Work done is 0.
Work done is 0? Okay. Here, come. Please close the door if possible. Okay, so
Work done 0. Considered.
So obviously one approach is, as he says, is to find out whether the work done in this closed path while moving the electron from the origin back to the origin in this closed loop. See, the closed loop doesn't have to be a circular loop. It's any path. So this is a square closed loop.
But it's not.
It might be a zigzag path like this and start and end up at the initial point. That's also closed. So the idea is that work, which is F dot dl, I've been writing it as ds yesterday, but dl is okay. If it's equal to 0, this circle here is what it goes to. If that's equal to 0, then it is conservative. If it's 0, then only it's conservative. I think you did the calculation and thought that it's non-zero.
Zero ne.
So we'll just check that. So this is the condition that we are going to verify. Okay. So given this force field and given this force, is the problem clear? You want me to repeat the problem? Yes. Okay, sure. Yeah, let's speak up. I mean, I need to know as well that whether it's you're actually connecting to the problem at all or not. In case of, again I repeat, no question is a silly question. And here you are actually asking the question again. No way it's silly. Okay? So please open up at any stage. Okay, so I'll repeat the problem again. So you're given an external force which is a function of x. That means that if you move along the positive x-axis, not along the x-axis in general, the force is changing in a linear fashion. Although it's directed, the direction of the force is along the y because it's j-cap. So if you ask me what's the force at x equal to 0, right here, it's just 0. If you're at x equal to L, it would be c times L, but the direction of the force is always that. So that's the error of the problem. So it's a function of along the x-axis. Now in this force field, what you're doing is you're moving an electron. You're moving an electron along this closed square loop. So you have started from the origin 0, 0, moved a distance L. Once you have hit L, x equal to L, then you travel straight up to L comma L, and then back to 0 L and come back to the origin. So you have completely traversed a closed loop. Now the question being asked is whether question to which Charan has already answered. Yes. But actually the answer is no. We'll see how it goes. Okay, so the question is whether this force is a conservative force. So what we learned from yesterday, go back to your notes yesterday, one of the conditions that you can verify whether the force field is a conservative one or not, if you do a closed path, if you traverse a closed path just like this, and find out the work done. What is the work done? It's just F dot ds or F dot s, F dot l, whatever you choose. S, L, they are equivalent. Displacement is all I need. Okay? And do it around a closed loop. If the answer is 0, that means the work done is path independent. If it's not 0, then it's actually path dependent. So we'll verify this condition. So that would be here. So what we can do is, we can split up this path into 4 parts. So the first one would be from taking the electron from 0, 0 to L comma 0. The second one would be this vertical one. The third one from N comma N to 0 comma N. And the fourth one would be back to the origin. And as we know that work is simply a scalar. So if you add algebraically each of the legs, work done into each of the legs, each of the paths and each of the sides, then it should give you the total work done. So that would be equivalent to this entire integral. Okay? Is the approach clear? Okay, so let's find out W1. W1 would be for the first leg from 0, 0 to L. So go back to the basics. It's F dot dl1. Okay, I'll call this vector here to be an elementary length along my direction of motion of the electron to be dl1. So what is F dot dl1? Before doing any integral at all, see F is this. Let's see x is a varying one here. X j dot, what is dl1? It's dl1, the vector dl1 is dl1 I cap. Got it? Because it's just along the x-axis. So it picks up on I cap. What is I cap or j cap?
0.
It's 0. So there is no work done, at least for the first leg. So without doing any integrals, just because the dot product has vanished, the work done is 0. It's the same example as we discussed yesterday. If you hold a block of mass and travel parallel to the earth, then the work done is 0. Because gravity and displacement are perpendicular. It's the same thing. Okay? Let's move on to the second leg. Again the marker. Let's try out this one. So W2. So let's work out f dot dl2 now. Of course there are integrals here. Integrals. But here we didn't really care about the integral. I mean, it wasn't to be evaluated because automatically the dot product just gave us 0. Okay, so now we'll do f dot dl2. So this is my dl2 vector. An elementary unit, an elementary length vector along
Y-axis.
the y-axis. So dl2 would be dl2 j cap now. Just the direction of the force. Now what is the force here? You are not changing the x. You are sitting at x equal to L and just
Changing
taking the electron from L comma 0 to L comma L. So what would be the force here?
CLJ cap.
CLJ cap. That's right. Does everyone get that? Because at x equal to L, what is the value of x at x here? It's x equal to
L.
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 If you do not change x and keep on traveling along the y-axis, then you have a constant force whose magnitude is just c times L. So the force that comes in here is c times L j cap dot dl2
J cap.
j cap. And the integral is to be done from where to where? Obviously,
L
from
comma
this
0.
point to this point. The starting point to the ending. So it's from L comma 0 to L comma L. Now L comma L, this is basically doing the integral from
0 to
from
L.
0
To L.
to L. Because L2, dl2 is changing from 0, take the y value from 0 to x is not changing. Okay. So it's so you can take out the constant factors outside the integrals as you usually do. J dot j is just 1. Okay. So it's just dl2. So that will give you
CLL2.
CL squared.
Okay.
So that's the work done due to the second leg. What about the third one? First of all, is this
This is
part clear? Yes.
Yes.
Why I have kept x equal to L here? Because it's a constant x. I mean, you're just changing along the y. So just replace x equal to L. Okay. So for the third leg, W3, it's again the same as this one.
W1.
But rather, dl3 will pick up a minus I cap. Right? So it's very similar to the first one. So it's f dot dl3, again the integral, but f is c, whatever it is, x j cap dot dl3 minus I cap. Because you are moving along the minus x-axis. But again, j dot I is 0. So this will again vanish. So for the third leg as well, similar to the first one, the work done is 0. What about the final one? Fourth one,
minus j cap.
square.
so it will be,
Minus CL square.
let's do that. Okay. So C times and C times 0 already, right? Because you're right there at x equal to 0. See the x coordinate. Along the y-axis, any coordinate for x would be 0, right? So it will be just C times 0, which is 0. That is to say that there is no force existing because of the functional nature of the force. There is no force if you are just sitting on the y-axis. So that's so automatically due to the functional dependence of the fourth leg does not contribute to any work done. Do you get this? So all I've done is split up the entire loop into 4 legs, evaluated the work done into each of the legs, but do understand that it gives 0 for the first, third and fourth. For the first and third, it's effectively due to the direction between the displacement and the force. You see the dot products have become 0 here. But for the fourth one, it's not due to the directional nature of f dot dl, but due to the functional dependence. Because right here, what you're doing is you're taking the electron from here to here, maintaining the same x. And what is that x? X is 0. Put x equal to 0 here, the force vanishes. So anything you do along the exact y-axis here will give you 0, just because our function provided or the force provided is this thing. Okay. So now what we do is we take the sum of all the works done. And since all 3 are 0, so the only contribution to the total work. So basically, just summing up these being scalar, I do not need to care about directions and all. Work and energy, these are just scalar quantities as well. So this is just CL squared. Okay. And this is nothing but this integral actually. It's a closed loop integral. So what does that give you? It gives you a non-zero value. Because L is obviously a non-zero quantity, it's the side of the square. It's a non-zero quantity. And C is something positive. So this being a non-zero quantity tells you that the force is non-conservative. Right? You got that? So I think you just thought that it's non-zero then it's conservative. No. So that's the path independent feature. If it had been path independent, if this force had been path independent, then it would have given you 0 and you could have claimed that it was a non-conservative. Sorry, conservative. Is that making sense? Okay. Had you taken a gravity field here, or the electrostatic field, then obviously due to the nature of the force again, it would have given you 0 because it's a conservative force. So having a functional dependence, it depends upon the nature of the function. So gravity is also an x-dependent or an r-dependent force. It goes as 1 over r squared. Or electrostatics, it also goes as 1 over r squared. But there, if you do the calculation, you can try it out. You do a calculation like this, in this closed loop. Imagine this to be an electrostatic field. Okay? And do the same calculation with 1 over r squared. You will see that it comes out to be 0. So it all depends upon, it can be a functional dependence of space, like you have here. But if the functional dependence is such that if you do the integral, the closed loop integral by doing the work done and so on, it gives you 0, then it's a conservative. This is just to emphasize the fact that having a functional dependence does not automatically tell you whether it's conservative or not. You have to actually do the calculation in order to find it. And this is the key, that it's path independent. So this kind of a force you cannot really write down as a gradient of a scalar potential energy. Any questions here? Good.
Source లేకుండా అక్కడి నుంచి
So let's move on to another problem. Let's see, this is now
ఫోర్స్
example
లేదు,
2.
ఫోర్స్ జీరో ఉంది. ఫోర్స్ లేకపోతే ఇక్కడ నుంచి ఇక్కడికి ఎలా మూవ్ అవుతుంది ఎలక్ట్రాన్? ఇట్స్ ఎగనెస్ట్ లా ఆఫ్ ఇనర్షియా కదా. Unless there is an external force acting, body will just face it as law of
What
inertia.
is the smelling of yesterday's deal? You cannot sense it from there, and sense it from here. Okay. So here is another problem. This is something called this potential that I will talk about. Something called the Lennard-Jones potential. Okay. So the form of the potential energy is something like this. Let me write it down and then I'll explain things. So you have seen several kinds of potential energies maybe. If not several kinds, but at least the electrostatic and the gravitational, which goes as 1 over r. So this kind of a potential called the Lennard-Jones potential typically appears in interatomic potentials. Suppose you have a diatomic molecule where the interparticle interaction, the potential or the potential energy, we call this the potential energy, can be written as this kind of a function, where r is the distance between the two molecules. So if you plot this function, u of r as a function of r, this is r equal to 0, and the function will look something like this. You can use a computer to do this. So it starts off, see, you can read it from the values of r. So what happens if you have very small r? That is, if you are somewhere here. If you are very close to 0, that is r is small, then 1 over r to the power 12 will dominate because r is very small. Then this part will pick up and you will have a positive potential. Now, if you are wondering about what sigma naught a and d are, these are just constants. And what kind of constants should they be? From dimensional analysis, you can make out that a needs to have a dimension of
R.
n to the power 12, n to the power 12, because this thing is r to the power 12. B should have a dimension of n to the power 6, and sigma naught will have the dimensions of energy. It's a potential energy. But these are constants. We do not worry about the constants as such. They are given, sigma naught a and b. So what we have to find out from this potential is first of all the force. Number one, we have to find out the force. So find f as a function of r. That's number one. Number two, find the position of stable equilibrium. Stable equilibrium. So these two would be the questions that will be answered. Okay. So now, rather than telling you about so now it's the same concept of conservative forces that we learned about. If you have a potential which is given to be this, and it's told that it's a conservative force, then F can be written as a minus gradient of U. Again, go back to yesterday's notes. That's one of the concepts or fundamental ideas of conservative force fields, that you can write down the force as the negative gradient of a scalar. So the first thing is easy to do. So number one, in order to find out F, you just have to do du dr r hat. Because the force is only, the potential energy is only dependent on r. Had it been dependent on theta and phi and so on, then this wouldn't have been possible. You just write it as minus du dr. Then the gradient would have terms of del theta, del phi and so on, along with factors of 1 over r. You go back to your notes on spherical coordinates. There you will see it was given as a homework exercise to find out the gradient in spherical polar coordinates. Anyways, so this is just r dependent. So this is this symbol. It's minus u. So it's just an exercise of taking derivatives. So sigma naught stays as it is. And what do you get from this one?
Minus 13a by r bar
Minus 12
a
over r to the power 13
plus
plus
6b
6b
by r
divided
bar
by r to
7.
the power 7 along with r hat. So this is just the force. It was just a one-line exercise. Now how do you find the stable equilibrium position? It's going to rain, right?
It's raining, already raining.
Good, good. You need some rain. Okay, so what's the idea of a stable equilibrium point?
Same force.
So what is it? What do you mean by equilibrium first of all?
Balanced forces.
Exactly. So whenever you have equilibrium, the idea of equilibrium is the net, the sum total of all the forces acting on the object should be equal to 0. Right? Do remember this thing, that equilibrium is different from something called steady state. Suppose you have current flowing in a wire. Is that equilibrium or steady state? That's steady state. Why? Because there is a net force. The force being the electromotive force, the potential difference. That's already there. But there is a stable current flowing. So that's a steady state situation. But the equilibrium situation is when the net force acting on the system is 0. So likewise, where do you think, following this potential energy profile, where would the force be 0? In this figure here, in this graph here, where do you think the force is going to be 0? Huh? Here? Okay. In order for the force to be 0, what do you think this one should be?
0.
Could we just close the fence? Lights are fine, right? Okay. Yeah, let's get back here. Although the nature is beautiful as of now, let's get back to the nature here. This is also nature. This is also nature. Okay, so if the force is to be 0, in order to find out the equilibrium position, the force needs to be 0, as we just discussed. So if you put this to 0, then the corresponding r that you will get from this expression, by solving this expression, should tell you where the equilibrium position is. And it won't be there. Let's see that it will actually be here. Okay, so this point needs to be clarified. Where in the potential energy profile would you expect the force to be 0? What is the force? It's the gradient. It's the minus du dr. Where do you think du dr could be 0 here? It could be 0 right here. Because
negative gradient.
if you take ddx is what? It's the gradient. If you consider a straight line, y equal to mx plus c. Could you have some silence here, please? Hello? Some silence here. The class is going on here. So, please. Okay. So, if you take the gradient, what is the gradient?
Slope.
So, go back to the equation of a straight line. Take dy dx.
Yeah.
Just yet. What is this?
Slope.
Or?
Gradient.
Exactly. It's the same thing here. You're taking the gradient of the potential energy function. Wherever the gradient would be 0, the force would be 0. It may or may not be a position of stable equilibrium. That will come to later. But in order to find out the equilibrium position, at least du dr should be 0. So, number 2, again the mark is out. Shift to my last one. So all we are doing now is putting f equal to 0. That means this expression, just put r equal to some r naught. R naught is the equilibrium position. So sigma naught
A equals
times minus
R naught
12 a
divided
over r naught. R naught to the power
13.
13 plus 6b divided by r naught to the power 7. This should be equal to 0. Does everyone get that?
Yes.
Now solve this for r naught. Solve for r naught.
2a by b.
What does that tell you?
2a by b whole power
2a
by b.
to the power
1 by 6.
1 by 6. Good. So this is the position where the force would be 0. And you see the position is right here, right at the bottom. So this is your r naught. So the value of r naught in terms of all these parameters we have just figured out is 2a over b to the power 1 by 6. So that's my equilibrium point. Now this should already kind of you should already maybe start thinking about this problem. See, du dr might be 0 in multiple positions. Well, this is a pretty simple graph where you just have one minima. You can see that. But suppose you have a profile like this. Something like this. If something like this would have been your potential energy. Like du dr would have been 0 right at the maximum, here, at multiple points. So which one would be the stable one? The stable one, for the stable one, it should at least be a minimum. Forget about the other maxima, other minima. Let's say the potential is something like this. So it has a maxima, it comes down and goes up again. So if you do this kind of a calculation for this kind of a profile, then it would be 0 here, 0 here, and 0 here. Which one would be the stable equilibrium? For stable equilibrium, which one? How do you define a stable equilibrium as compared to an unstable equilibrium? Well, du dr would be 0 for, as you know from simple calculus, du dr or du dx would be 0 for maxima as well as for minima. All I am saying here is, we have done it for the minima, but for the maxima as well it would be 0. But those won't be positions of stable equilibrium. That you can verify by taking the second derivative. Go back to your elementary calculus of maxima and minima. The second derivative, if it's positive, it tells you that the curve is actually a minimum. If it's negative, it's a maximum. Right? The positions of minima would actually be the points of stable equilibrium. Why is it stable? Because if you perturb, if you disturb the particle from this kind of a position, it will prefer to stay back here. But if you do it here, it will either topple to the other side, to the left or to the right. So that would make it unstable and stable here. Is the idea clear of stable and unstable? So it's like you disturb the particle, which is already sitting here, slightly. If it prefers to come back there to that minimum position, then it's stable. If you disturb the particle already here, then it will either prefer to go to the right or to the left. Then it's unstable. Okay, so this is my position of stable equilibrium given by this R type. So what you were saying is the position being here. See what happens here is the potential itself goes to 0. You see the UR curve crosses the x-axis or the R-axis here at 0. So here this point is basically the point where U becomes 0. So you can find out that point again by putting this equal to 0. So A over, let me call this point what? Let me call this point Rn. Rn to the power 12 minus B over Rn to the power 6, that will be equal. So this Rn, if you solve for this Rn would give you the position where the potential itself is going to 0. But that's not a position of a force equal to 0. Force equal to 0 will only happen when the derivative goes to 0 of the potential. So that only happens here. But keep in mind, for a more complicated, not complicated, but for a more extended kind of a potential profile, like the one I have drawn there, which has several maxima and minima, then in order to find out the stable equilibrium position, one has to go an order high in derivative and find out the second derivative such that you are confirmed that it's a position of minimum. Okay. So this potential in itself is kind of very interesting. Why is it interesting? See, if you take the slope here from here to here before it has started bending, in this part, what do you think the gradient is?
Cons.
It's
negative.
Negative, right? It's negative. Why? Think of a straight line. Although this is not a straight line, but just think of a straight line which is like this. What is the gradient? It's less than 0. Right? So if it's less than 0, then the force is what? Force is minus du dr. So du dr itself is negative. The force is positive. That means the force is repulsive. So when the particles are actually sensing a distance which is of this order, that is very low in R, very close to each other, they are feeling a repulsive force. Now you cross the minimum here and go here. Then the slope is just what? Slope is taking the tangent at that point. Then it's always positive. That means du dr being positive, the force having a minus sign is negative. That means the force is attractive. So after the interparticle distance has increased beyond this, the forces start becoming attractive. So this is a potential which combines both the repulsive part and the attractive part. And this actually happens when you consider interparticle interactions in typically diatomic molecules. Diatomic, you know? A molecule having two atoms, diatomic. Di is two. Okay. And another very common example for this is the spring force, which is again a conservative force. If you extend the spring by a magnitude of x, what is the potential energy?
K into x.
K into x is the force. What is the potential energy? Half kg. Right. So if you have a spring spring potential energy. Let me write that as ux. We have been using u as potential energy. So it's half kx square. So what is the profile if you draw the graph? If you plot u as a function of x, what does it look like? Parabola. Good, good. What kind of a parabola? Exactly. Good. Very good. So you see at x equal to 0, the graph will pass through 0. Put x equal to 0, u is 0. Now both for x negative and positive, u is always positive because it's an x square sitting. So it's a parabola pointing upwards. So it's like this. Right? Now for x less than 0, that is in this half, you find out force is what? Minus mu dx? Right. So it's minus kx. So this is the minus kx that you see in Hooke's law. Right? So that comes from basically if you take the gradient, it's all in the same framework. You take the gradient of the potential energy that gives you the force, minus kx. That's standard spring force, which is basically the basis of Hooke's law. If you strain, for low strain, the force is proportional to the stress is proportional to the strain. So that's the statement of Hooke's law. So for x less than 0, this will turn out to be positive, right? That will tell you that if you compress it too much, it will try to restore it back to the equilibrium position. And where is the equilibrium position? Just like we had it here, it will obviously be here. There is no point of unstable equilibrium here because there is no maxima in this plot. So it will always have a stable equilibrium, and that equilibrium is basically the unextended length of the spring, the relaxed position of the spring. If you extend it too much, then it goes beyond x greater than 0. Then also it will try to restore it back because of this minus kx sign. So compress it, it tries to extend back. Extend it, it tries to compress back again to where? To this equilibrium position. Now, had you shifted the parabola a bit by saying that the relaxed position is not at x equal to 0 but at x equal to x0, then all that will happen is the parabola will just shift to a new minimum, x0. So then the potential energy will look like half k x minus x0. Same exercise but with a shifted minimum or a shifted equilibrium position. Okay. Any questions here? Especially on this part? Okay. Good. Let's quickly do another simple problem. This problem will involve friction, which is a non-conservative force. So till now we have been dealing with conservative forces. So let's quickly do a simple problem on friction and convince ourselves that friction is actually a path-dependent force. Okay, so imagine a situation like this. You have a block of mass 20 kilograms and you are dragging it along the floor. You have started from a point A and you have to move the block to a point C. There is a straight path here which is of length 2.5 meters and there is an alternative path going by a B, and this is 2 meters and this is 0.5 meters. That is, from A to B is 2 meters, from B to C is 0.5 meters. Now, figure out whether these two paths, A to C via B and directly from A to C, whether they give you the same work done due to friction given that the coefficient of friction is point between the ground and the block surface. Okay. So what do? We find out the work done from A to C directly, that's one. And number two, we find out the work done A to B to C. Had these two work dones been the same, then friction would be conservative. But you can check for yourself. How do you find out the work done due to friction?
Nu n.
It's mu times n is the force.
Friction.
The force of friction is mu times n. What is n? mg.
200 meter per second.
Mu k here times mg. Now friction is an opposing force. So it will move. If you make a displacement towards this, then friction is actually acting towards the opposite direction. So it will become the F dot S will become a minus sign. So this will actually be, if you do it for A to C, this will actually be minus mu k mg times the displacement. The displacement is 2.5 meters. Then you obviously need to substitute for m, which is 20 kilograms, the g, which is 9.8, and the mu k, which is 0.2. So that gives you the work done if you move the block directly from A to C. This will give you a number, and that number would be in what? In joules, right? Because this is work done, work. So some joules. Likewise, do the same thing for A, B, C. You will see that the two numbers, you can do a quick calculation now itself. You will see that the two numbers are different. That immediately tells you that friction is a non-conservative.
98.
Minus 98. The first one. Okay. What about the second one? The second one needs two steps of calculation. A to B and B to C. So figure that out. In the meantime, I'll start taking your attendance so that we